So here we're going to look at another way of producing light, and we're going to use Faraday's law. Faraday's law is one of these really important laws of electromagnetism, and it's really actually quite simple. It basically states that if you vary the magnetic field, you can induce a current. And so imagine having a magnet. If you move the magnet around, it will actually create an electric field. Or if you have a wire next to a magnet, then by moving the magnet around this wire, it will induce a current inside this wire. So that's really the basic idea of Faraday's law, and I'm going to illustrate that sort of in a simple way. What I like to call the $5 ring challenge. So here I have my assistant Flora, and she will wants to earn $5 by being able to put the ring on these magnets. Okay, so it's pretty simple, but you cannot slide it with your hand. You have to drop it. So the idea is, so now you can take the ring, and the idea is to try to have the ring go over the magnet, and you drop it at not closer than, let's say, 5 centimeters, and then if you manage, you get the $5. Okay, are you up for the challenge?
Sure.
Okay, so let's see. So you drop it and you try to aim so that it actually falls onto the magnet. Let's see what happens. Okay, try again, and you have 3 tries. One more, 2 more. Well, I try again. So it didn't work. So that's so what is happening. So now if you feel it, and I'll let you feel it. So try to put the ring onto the magnet. What do you feel?
Oh, there's like a tugging sensation. It wants to go on like either one of the sides, I guess.
So you feel a resistance, no? When you move the ring with the magnet, you feel quite a strong resistance, and clearly the ring is not magnetic, and so, but by moving it, you actually feel quite a bit of a resistance going over the magnet, and that's what you call the Lenz's law, or it's also a consequence of Faraday's law, in the sense that when I move the ring around, it feels a changing magnetic field. So this changing magnetic field will induce an electric current inside the ring, which will actually repel the magnetic field from the magnet, and that's why it doesn't want to go on. So I'll give you one more try, and then see now and you can maybe film it from the top, so you can see that it's very centered, and then we'll try to see what happens to the ring when you drop it. And, there's really no way it really actually wants to go on top, so you can try many times, and she will probably never manage. And that's basically the thanks to Faraday. Thank you. So in this little game, we saw a nice consequence of Faraday's law and this induced current inside a ring. But can we do something useful out of it and not just play games? And so for that, I'm going to take this Faraday lamp. So let me show you this lamp. Yeah, we're going to use actually Faraday's law to generate light. So I'm going to show you what happens if I turn the lamp around. You'll see there's a magnet which is going to drop through these big solenoids, and that generates light. So let me do this again. So here's the magnet. These are the solenoids, and when the magnet crosses these solenoids, or it will basically generate some electric current, which will transform into light. So let me turn it around again, and you see that. And for a short time, the magnet will actually generate this light. So if I do it a little quicker, you see that more and more light. I'm going to create the light, and if I shake it, the light stays on for a while because there's a sort of a small capacitor in there which keeps some of the electricity. And so that's really using the changing magnetic field, which creates a current, which can be used to create also light. So that's sort of a Faraday light, a flashlight. So to finish, we're going to look at another important source of light. And this is a laser which we're using quite a bit. So the laser is actually quite interesting. So it's the old lasers were these very big long tubes which were filled with some gas, let's say neon gas, and then you had two mirrors at the ends, and the light would bounce back and forth in these big mirrors and create this laser light. But nowadays, most lasers are, they're very small. So this is an example of a McGill pen laser, and where you can shine light, and this is a red laser. But they're basically not made of these huge tubes as before, but they're basically LED lasers. And so they're not very different from an LED. The basic principle of an LED laser is the same as the LED. You basically have to transfer energy from an electron into light. So an electron falls from a certain energy state to a low energy state, and that creates a light at that energy. But what is special in the laser is that you're going to actually confine the light between two mirrors, and so the light is going to bounce back and forth many times, so that it creates sort of a coherent light emission when it comes out of it. And the example here you see on the right is basically this sandwich of aluminum gallium arsenide, and one is doped with like a p-type, which is lack of electrons, and the other one is an n-type, that's why it's called N, that has an excess of electrons. And so by putting a voltage between these two layers, you're going to transfer an electron from one side to the other, and by doing that, that electron will lose energy and will emit light. And once the light is emitted, it will be trapped between these mirrors, will bounce back and forth a few times until it reaches a certain threshold in power, when it basically then moves out towards the side. And so that's kind of the principle of an LED laser. And you see the difference on the bottom graphs in terms of the light which is emitted. So an LED is relatively sharp, but it has sort of a finite width, whereas a laser, you see on the left of the right plot, it's going to be incredibly narrow. So the emission line, in this case, let's say there's an example of 450 nanometers, it's going to be a very thin line of spectrum, and it's only photons or only light coming at that wavelength which is coming out of that laser. Whereas in LED, it's a little broader. So the mechanism is not incredibly different, but uh, what is special for laser, it creates this very narrow uh, window of color which comes out of a laser. In addition, all the light coming out of the laser is in the same phase. So all the electric fields inside the laser light, which is made out of particles which are photons, they all move sort of, they vibrate, or they basically move together. They oscillate in the same was the same oscillation. And whereas in LED, they might actually oscillate in this way randomly and so on. And so a laser has this coherent light where basically things move sort of in this very coherent way. And that has important consequences, which we'll show you in this in this nice demonstrations here. $20 bill, and what I'm going to do, I'm going to take a powerful green laser and shine through the $20 bill at this spot where the maple leaf is, and then we're going to see what you actually see in the refraction pattern through that $20 bill. And what you can see is you can kind of pretty clearly see the $20 sign, and that's from this grading which is produced on the $20 Canadian bill. So because we had this laser, which means that you have the waves, the electromagnetic waves, they all move in the same sort of coherent way, and if that comes onto this $20 bill, and it's actually true, it was a $5 bill, a $50 bill, or a $10 bill, but except in the $10 bill you'll see a 10, and a $5 bill you'll see a 5, and a 50 you'll see a 50. And so when this coherent light is hitting this grading on the money, then it forms this refraction pattern which you can only see when you have this coherent light going through. So it's kind of a nice illustration of what is special with the laser. So if I did the same thing with an LED lamp, I wouldn't actually be able to see this pattern. And so with this, I will conclude our video on light, and I hope you enjoyed this video. Thank you.